So I'd like to go over a simple problem of finding the electric field as a result of multiple charges. Let's work on a problem, for example, that has 3 charges. Okay, so the 3 charges here, I'm going to call them Q1 with magnitude of minus 5 microcoulomb, Q2 that has a magnitude of plus 10 microcoulomb, and Q3 which has a magnitude of plus 6 microcoulomb. I have to provide you the coordinates for each of these, so let's just pick some random coordinates. Let's say that Q1 is located at 4 centimeter, comma 3 centimeter. Q2 located at 5 centimeter and minus 5 centimeter. And Q3 is located at, on the x-axis, let's say, so 10 centimeter and 0. Okay, so now that we have these, let's write the goal of the problem. The question asks you to find the net electric field at the origin. So the goal is to find the net electric field at 0, 0. Go ahead and pause the video and see if you can solve this problem on your own, and then come back and we'll go through it step by step. Okay, so let's start by drawing. So the first step is to draw, and it's actually a very important step. You need to make sure you can do this step correctly. So you don't have to use a ruler, but try to just draw as straight as possible. It's very important to have a good drawing. Okay, so this is my x-axis, that's my y-axis. I know that, okay, let's place the charges on this. I'm going to use blue to place the charges, and I have a, which one do I start by drawing? Now, this is also common sense that you start with something that is furthest from the origin so you don't run out of space at the end. So it's best to start by drawing Q3. So Q3 is located at x equals 10 and 0. So I'm just going to pick this point, the furthest point, as the location of charge 3, right? And you could either draw the distances if you want on this, or you could just write the coordinate next to it. I could just put something very small here and call this 10 centimeter. Now, the next charge that's easy to draw after this is 5 minus 5. Now 5 is half of 10, so I'm going to just aim for something in the middle here. Let's say I put it here. Now, this would be Q2, which is plus 10 microcoulomb. Now I'm going to put the last charge, Q1, which is at 4, 3. Now, if it's 4, 3, remember, if you're saying this is 5, then 4 has to be behind it. That's the level of precision we're expecting. So I'm just going to draw 4 here. And so, like that. So this would be my Q1, which is minus 5 microcoulomb. Now let me draw the coordinates for all of these. We're saying that, again, one way to do this is you could just say that P2 is equal to 5 centimeter minus 5 centimeter. Or, since that information was already written here, if it's clear, then instead of that, you could just show it geometrically, because that's at the end what you're looking for. So This is 5 centimeter. And this is 5 centimeter. This is 3 centimeter. And this from here to here is 4 centimeter. So I'm gonna put it here. Okay. Now that we have all the coordinates, the next step, which sometimes is explicitly mentioned, but most of the times in these problems it's not actually mentioned, but you have to do it. That is, draw a schematic of each of the electric fields, because the question is asking you to find the net electric field. So you need to find each of them individually so you can add them up. So you can pause the video and see if you can do this step. But basically the way you should do it is, let's just start from Q1. You are going to connect, or if you could do it by hand without doing this step, that's fine. But I'm just going to show you the thought here, is that the point of interest is the origin. So I'm going to lightly draw the line that connects the origin to Q1. And I know that the electric field is going to be on that line. Okay, the electric field is going to be on this line. Now, because my charge is negative, the electric field is going to be pointing towards my charge, which means that E1 would look something like that. Okay, done. Now I'm going to do the same thing for Q2. Now in this case, Q2 is positive, so the electric field would be pointing away from the charge. Q3 is also positive, and it's on the x-axis, so the vector for the electric field due to Q3 is going to be also on the x-axis, but it's going to be pointing away from my charge. So it's a vector that's pointing in this direction on the x-axis. Okay, so we're done with the most important step in the problem, which is setting it up and having the drawings. Now, we are going to go to the next step, and that is use the superposition principle to find the net electric field, which just says that the net electric field is just the sum of the individual electric field to the charges. Okay, so this kind of just tells you that you need to find each of these electric fields, and in order to find them, the first step would be to use the Coulomb's law to find their magnitude. So I'm going to put E1 magnitude symbol to differentiate it with the vector E1, and then I'm going to use the Coulomb's law, which is K times Q1 divided by the distance between between Q1 and the origin. Now, if you look at this triangle right here, there's a triangle here, right? This side is 3. The other side is 4, and so this triangle. This is 90 degrees. One side is 3, one side is 4. R1 is the hypotenuse, which you use the Pythagorean theorem to find. Okay, so then R1 is just 5 centimeter basically, but I'll write it down. So K, it will be given to you. It's about 9 times 10 to 9. Now, I don't actually memorize anything. So I always forget the unit for these things because I just don't memorize them. So, but I do remember the Coulomb's law. So if the force between charges is K times Q1, Q2 divided by R squared, and I know the unit of each of these, right? So I know that force is Newton, R is meter, so I have a meter squared on this side. Each Q is in coulombs, so I have Coulomb times Coulomb, which is Coulomb squared. Then that tells me that the unit for K must be Newton divided by Coulomb squared multiplied by meter squared. Now, again, the units will be given to you with the constant, but it's good to generally know how to use dimension analysis, which was covered in the beginning of 131. Okay, so the unit for this is Newton times meter squared divided by Coulomb squared. That's K. Q1. Now here, I forgot to write this correctly. What I'm actually going to plug in is the magnitude of the charge, not the sign, because I'm trying to find the magnitude of E1, which is always a positive number. So it doesn't make sense to put negative numbers on the right side. Okay, now Q1 is minus 5 microcoulomb, so its magnitude is 5 times 10 to minus 6 coulomb divided by. Now, R1 squared is the x component squared plus plus the y component squared, so it's basically 4 centimeter squared plus 3 centimeter squared. Now, if you calculate this, you get 25 centimeter squared. Okay. Now, you can plug in all the numbers in a calculator. I'm just going to do it by hand here, real quick. So what we have here is I'm going to collect all the numbers, and I'm going to collect all the powers of 10 separately. And then I'm going to write my units. So first, all the numbers that are not 10, or powers of 10. I see a 9 and a 5, that's 45. And I have to divide by 25, right? Now the only thing that's left is powers of 10, so multiply by, now there's 10 to 9, 10 to minus 6, so I'm left with 10 to 3. Now I'm going to cancel out my units, so pay attention here, and this is why it's very important to keep track of the units. One of the C's is going to cancel out the C, and then you have to deal with the division of meter over centimeter. So I could have plugged in this number here already in meters right from the start, so then they would have canceled out. But because I'm using centimeter, they're not canceling out. And this is why we write the units, because they'll stop you from making mistakes when it comes to unit conversion. So then remember that that 1 meter is 100 centimeter. So a meter over centimeter is 100. So meter over centimeter squared is 10,000, or a factor of 10 to 4. So I get a factor of 10 to 4 coming from this unit conversion in addition to my power of 3 here. So that's just coming from unit conversion. Then the lengths would cancel out, so my final unit is just Newton divided by Coulomb. It is very important because now you say, okay, I have the right answer and I converted the units correctly because I checked the final answer unit and it's correct. Okay, now what is this? My trick, again, you can use calculator, but my trick is just to turn this into 100. Multiply by 4. So this is 180. So I basically have 10 to 7 here. I have 180 here and 100 here. 180 over 100 is 1.8, and I have that. So it's 1.8 times 10 to 7 Newton per Coulomb. Feel free to use your calculator for this part. Okay, we're done with finding the magnitude of one of them. Let's just do this again for charge number 2. You can pause the video if you had issues with finding E1 and you want to try doing E2 yourself. Now Q2 is plus 10 microcoulomb. So that's 10 times 10 to minus 6 coulomb. Now let's think about the distance. Charge 2 is located at the coordinates 5, 5, 5 minus 5. So the distance, R2, is square root 5 centimeter squared plus 5 centimeter squared, which is just 5 centimeter multiplied by root 2. Okay, so R2 squared is just 50 centimeters squared. So that's 50 centimeters squared. Again, I pay attention to the units, how one of the c's cancel that out, and I have meter and centimeter, so I have to take care of that. Every time I have meter over centimeter squared, it gives me a factor of 10 to 4. So let's collect all the powers then. I have 10 to 9 here, and I have 10 and 10 to minus 6. So this is a power of 10 to 4, right? And I have a 9 sitting there. So it's 9 divided by 50 and 10 to 4. I have my Newton, one of the coulombs, and I just forgot to do the conversion yet, right? So there's meter over centimeter squared. So if I forgot, that's fine. You write it here, and you remember to take care of it. You have to get rid of this meter over centimeter, and that's the reminder when you write the units. Again, I'm going to turn the denominator on this side to 100 by multiplying it by 2. Then that means this is really 18. Okay, so what's going on here? Now this is a factor of 10 to 4. All right, so now let's collect everything. That's 1.8. There will be, I divided it by 10, so this is just 10 in the denominator. So, okay, we have 4 and 4, 8, divided by 1, 7. So it's 1.8 times 2 10 to 7 Newton per coulomb. All right, it's the same magnitude. You see this? Same magnitude. Now the question is, does this make any sense? It is possible that you are actually asked that question explicitly, then you have to answer it, but this is really just for your own understanding and making sure you did everything correctly, because it's a bit suspicious, at first to think, or even if they were different, you would think which one is bigger than the other one. So you're going to come back to your problem here. You see that Q1's charge is half Q2. So, okay, if I look at the Coulomb's law, I see that if you halve the charge, the electric field should halve. But if you look at the distances, specifically the distance squared, Q1 is at 5 centimeters squared, which is 25, and Q2 is located at 50 centimeters squared. So there are squareds scales as, so let me just quickly write this on the side, just as a side note. So I'm saying the magnitude of E1 divided by the magnitude of E2 is equal to, K cancels out, is the ratio of Q1 over Q2 multiplied by inverse ratio of their distances squared. So I'm saying that Q1 is half the amount of charge. So you have 1/2 times R2 over R1 squared, which is 50 centimeters squared divided by 25 centimeters squared. So this gives you a factor of 2, which cancels that one, so you get 1. And this is why you got the same answer. So the answer actually makes sense. Okay. So that was just a sanity check, really. And if you do this in your head, just by following these ratios in your head, when you come here, you just pause for a moment and you think, does it make sense? If it makes sense, then you're happy to next step. So let's find E3 now. All right, 9 times 10 to 9 Newton meter squared Coulomb squared multiplied by Q3 is plus 6 microcoulomb, so it's 6 times 10 to minus 6 coulomb. What is this distance to the origin? Well, it's just 10 centimeter away, so I'm gonna put 10 centimeter squared. Okay, now 9 times 6 will give you 54. This here is 100 centimeters squared. Okay, and I'm gonna write down the powers that I have. I have 10 to 9 and 10 to minus 6, so that gives me 10 to 3. I have a 100 sitting there. Now I'm gonna write my my units. So I have Newton divided by 1c times the factor of meter over centimeter squared, which remember, it's just 10 to 4. So this is 10 to 4. This is 10 to 2. So I have 3 and 4, 7 minus that. So it's really 54 times 10 to 6. Sorry, it's 54 times 10 to 5 Newton per coulomb. Or if I want to write this in the scientific notation, I would say it's 5.4 times 10 to 6 Newton per coulomb. Okay. Okay, so we have the magnitude of all three electric fields. Now, what's the next step? Remember that to find the net electric field using the superposition principle, we have to actually find their direction also. So the way here, use some basic vector statements or identities, and that is that recall that if if you want to add two vectors, so if A is equal to B plus C, then what this really means is that if A is made out of AX, AY, B is BX, BY, C is CX, CY, then in this notation, B plus C is equal to A is really the statement that says AX comma AY has to be equal to, as a tuple, BX plus CX comma BY plus CY, which means that they individually, the components add up and they're equal, which means that AX is equal to BX plus CX and AY is equal to BY plus CY. So these two lines are equivalent to the first line. Okay, so we're going to use this, except instead of ABC, we have E net, E1, E2, and E3. Now what this means is that we have to, I'm going to just put this behind here. What this means that we have to look at the goal of the problem again, which is finding E net, right? So E net x's component of E net is just E1x plus E2x plus E3x. And EY net is E1y plus E2y plus E3y. Okay, now what this means is you have to find 6 numbers in here. Okay, E1, E2, E3 in the x component and in the y component. So then you just start finding them one by one. Go ahead and pause the video if you know how to find these from the magnitude and the geometry of the problem. So let's focus on one at a time. Let's just talk about E1. Okay, what is E1x? So a little bit of geometry here again. I'm going to redraw what E1x looks like. What E1 looks like. So we had something like this. That's your x, that's your y. E1 is a vector that's pointing in this direction. Now E1 is caused by a charge that is located at the coordinates of 4 and 3. So the distance from here to here is 4, and the distance from here to here is 3. Now, this angle is 90 degrees, which means you have a 90-degree triangle and you can use tricks. So, in order to identify what the components of E1 are, first you have to look at the geometry of the problem and think about the angle that it makes with the positive side of the x-axis. I'm going to call this theta 1. Okay, now you have the triangle right in front of you, so it's very easy to think about the identities here, which are the definition of sine and cosine. Sine theta 1 is 3 over 5, and cosine theta 1 is 4 over 5. Now, if the problem explicitly asks you to find what's theta 1 in degrees or radian, then you would actually find them. But as long as you don't actually need to know what theta 1 is, you don't have to go there. All we need to know is the sine and cosine. Okay, now the next thing is, in this triangle, you can see that at least the magnitude of the x and y components in this triangle are just related to the sine and cosine. Now, there's some issues with doing this for any vector, and that you have to take care of a negative sign, which I'll show you for the other electric fields. But for now, everything will work out fine. So E1x is just the magnitude of E1, because that is the hypotenuse multiplied by cosine of theta 1, which is 4/5. So this is just 0.8, and I know what the magnitude of E1 is. It's 1.8 times 10 to 7 Newton per Coulomb. Okay? Now, if we calculate that, we should get 1.44, let's see, right, 1.44 times 10 to 7 Newton per Coulomb. Now, again, check your answer. Does that make sense? Well, it's 10 to 7, so it makes sense because you expect the same order, really, for typical angles. And what about its sign? It's positive, so it's fine. Okay, let's do E1y. So that's E1 magnitude again times sine theta 1, which is just 0.6. So that's 1.8 times 10 to 7 Newton per Coulomb multiplied by 0.6, which is 1.08. And you pay attention here, there was no need for any rounding so far. Times 10 to 7 Newton per Coulomb. Okay, good. Now I'm gonna write the x and y component of E2. So let's look at the situation with E2. So E2 is pointing in that direction. So let me redraw it here. I just don't want to make the figure too crowded. So if this is E2, basically it's going to be the hypotenuse for some triangle here that we're trying to find the angle for. And it's the continuation of a line that was connected at 5 minus 5. So this triangle right here, this upper triangle here, the angle that is sitting right inside here, that angle, let me just call it alpha for now. This angle alpha is part of this triangle 5, 5. So now why do I care about that? Because if I follow it on this side, this angle is also alpha. Now what I care about is really the angle that E2 makes with the x-axis. That is this angle. Okay, I'm going to call this theta 2. Now theta 2 and alpha, they add up to 180. Okay, so they're related to each other. So if I know the properties of alpha, then I know the properties of theta 2 basically. Now alpha is part of this triangle. Okay, what alpha is really 45 degrees, right? Because sine of alpha is 5 divided by 5 root 2, which is 1 over root 2, or root 2 over 2. And it also is the same as cosine alpha. It's 45 degree angle that has the same sine and cosine. Okay, so this is really 45 degree. And it means that this must be 135 degree. Okay, now again, you don't really need to actually calculate these angles, because all you really care about is they have this relationship, and whenever they have that relationship, their sine and cosines are related in a way that their sines are equal, but their cosines have a relative minus sign. Okay, and this is all systematic. If I was solving this problem on my own, and I was not explaining it to you guys, I would only calculate alpha, and I wouldn't really think about theta 2. Instead, I would put a minus sign by hand because I know E2 is pointing in a negative direction of x. So whichever way is easier for you to understand. But let's go back here, and I'm gonna use blue. So what is E2x? It's the magnitude of E2. See, it's because I want to use the simple formula that doesn't have any extra, and there's no additional minus sign you have to put in this. If you follow this convention where you define angles only with the positive side of the x-axis. But if I was using 45, I would have to put a minus sign by hand in here. That's the only difference. Okay, so what I'm going to do here then is look up the magnitude, which is the same as 1.8, multiplied by cosine theta 2, which is minus root 2 over 2. And that's the minus sign I was talking about. So it really depends. Do you want to put the minus sign there, or do you want to start by putting the minus sign behind it and instead look at alpha instead of theta 2? That's the difference. Okay, now, well, what is this? This is basically, if you want to write it in in this form with the square root 2, it's really 1.8 divided by 2 is 0.9. With a minus sign, don't forget that, root 2 times 10 to 7 Newton per Coulomb. And we can actually calculate this. Let's see. So we have 0.9 multiplied by square root 2. So this is minus 1.2728. And I'm keeping extra digits here because remember, we don't want to round too early. 10 to... I would keep this as square root 2 until the last step, to be honest, just because of that. But I just want to show you the numerical value. Okay. Now, what about the y component of E2? Well, same magnitude times sine theta 2. Now, sine of 45 and sine of 135, they're the same. In fact, whenever the two angles add up to 180, their sines are equal. So it's 1.8 times 10 to 7 Newton per Coulomb multiplied by plus root 2 over 2. So there's no minus sign here. Okay, then that means that I get exactly the same answer as here, except the sign is flipped. So it's plus 1.2728 10 to 7 Newton per Coulomb. Okay, we're done with that. Now let's think about E3x. In a similar way, I'm going to define theta 3 now. I just have to redraw this real quick for you. That's x, that's y. The charge that caused E3 was sitting there, so E3 is really pointing in this direction. So that's my E3. And its angle, theta 3, see, if I was doing this purely geometrically and not paying attention to the sign conventions, I would say that the angle is 0. But the angle is actually 180 degrees with respect to the positive side of the x-axis. And that makes a difference. Why? Because sine of 180 is the same as sine of 0 and is 0. But cosine of 180 is minus 1. Whereas cosine of 0 is plus 1. You see, there's a sign difference, and again, this goes back to how you're comfortable with doing this calculation. Okay, so E3 is just pointing in a negative direction of the x-axis, and its y component is basically 0. So this is 0. Magnitude of E3 is 5.4 times 10 to 6 Newton per Coulomb, multiplied by cosine of 180, which is minus 1. So it's minus 5.4 times 10 to 6 Newton per Coulomb. Again, I'm trying to be really pedantic here, but you could have just said E3 is all pointing in the minus x direction, so I'm just going to write its magnitude and put a minus sign behind it, and that's it. All right, so now we have all of these guys. We go back to what the superposition principle and the addition of these vectors mean. I have to add the x components together, and I have to add the y components together, which means that my E net in the x direction is equal to E1x, which is 1.44 times 10 to 7 Newton per Coulomb, plus E2x, which is actually a negative number, minus 1.2728 times 10 to 7 Newton per Coulomb, plus E3x, which is again a minus number, 5.4 times 10 to 6 Newton per Coulomb. Now, if you add these numbers up, and if I did my math correctly, let's see, how are we doing this? So remember that you have to actually make sure the powers are the same. Here I have 10 to 6, so my option is to, for example, rewrite this as 0.54 times 10 to 7 so I can add the numbers, because then it's 1.44 minus 1.2728 minus 0.554, all of it times 10 to 7 Newton per Coulomb. Okay, let me quickly plug this in my calculator. 2728 minus 0.54. Okay, so this is minus 0.3728 times 10 to 7 Newton per Coulomb. So in scientific notation, I have to actually turn this into a number that's order, a number between 1 to 10. So it's minus 3.7, and I'm going to round it here a little bit because I'm really close to my final answer. Minus 3.7, 3 times 10 to 6 Newton per Coulomb. Okay, so I'm getting very close. I have the x component of the net field. Now I'm going to just do the same thing for the y component. EY net is, now what's E1y? E1y was 1.08 times 10 to 7 Newton per Coulomb plus E2y, which is positive, it's 2728, right, plus E3y, which is just 0. Now I'm going to add all these numbers up. Again, since the power is 10 to 7, 10 to 7, this just means that I have to add the numbers behind the power separately. It's 1.08 plus 1.2728, which should be plus 2.3528 times 10 to 7 Newton per Coulomb. And if I want to round this, I would round it as, now here's the thing, if you want to be consistent, this number here for the x component is actually 10 to 6, so it's actually smaller than 10 to 7. So if you really want to be consistent, pay attention to the fact that here you're including 2 digits behind 10 to 6. If I wanted to report this number, then I would think that I would actually should write it as 2.353 10 to 7 Newton per Coulomb. So I'm actually keeping 1 extra digit for this one. The reason for that being, well, this is 10 to 7, this is 10 to 6. That's why. Because this extra digit here is the same order as that 3 above, if that makes sense. Okay, so now everything is fine. I found the x and y components. Now, if the problem asked you to find the x and y component, you're done with the problem. If it told you find the net electric field without specifying anything about its magnitude or direction, you're done. But if the problem explicitly says find the magnitude, then you have to find the magnitude. You just use the Pythagorean theorem. The magnitude of the net field is equal to square root of its x component squared plus y component squared. Okay, so all we have to do is add these up. Let's see. So we're adding up 3. Okay, so EX net is 3.73. Right. 3.73 times 10 to 6. And Y is 2.353 times 10 to 7. So if I calculate this correctly, this will turn out to 2.38 times 10 to 7 Newton per Coulomb. Okay? So that's if the problem asks you to express this up to 2 significant figures, basically. Now, if the problem also says or uses the phrase find the direction, it's a bit ambiguous. I will try to avoid asking questions like that because technically if you know x and y, you know the direction, but I'll try to be more specific. Find the angle theta net that the electric field makes with the plus x direction. Okay, so we're thinking that I'm gonna draw a separate x and y here. We're thinking that E net is a vector. Mostly it's in the y direction, but it has a slight negative amount in the y. So it's kind of like this. So that's your E net. And you want to find this theta net. Question mark. Okay, remember, if you define it like that, then it's actually pretty easy to calculate, because according to what I showed you before here, according to these relationships, you know, just basic trigs and Cartesian coordinate, the E net, you can pick either x or y direction to solve this. They'll give you the same answer. Let's just go with the x direction. E net in the x direction. Actually, that's a very interesting point. Let me go back to that. So you have two information. You have the x component and the y component. So be careful. When you use one of them, your answer is not complete. And I'll tell you why. So, okay, basically what I'm trying to say is that if, say I didn't give you anything, this is x, this is y, and I tell you to use the information that the x component of a vector is equal to a certain number. What is its angle? Well, then when you draw it, you'll be thinking, okay, all you're telling me is that the x component of a vector is here, which means that this vector could be anywhere starting from the origin as long as its tip ends up on this line. It could be that, or it could be that, or it could be that. So there are infinite solutions, right? Now I give you one extra piece of information, and that is I tell you, you know the x component. You also know the total magnitude of this vector. If I told you that, then you would have to pick the length to match that, which means this is not valid anymore, most likely. And you actually only, out of this infinite solutions, you only have two solutions. One is the one on top, one is the one on the bottom. both would be valid based on the information I gave you. Now, what's the difference between the vectors that's on top and the vectors that's at the bottom is their y component. So it's this point where you look at the y component, and just knowing whether it's positive or negative, well, or equal to 0, will tell you everything. If it's equal to 0, then this is your solution, really. If it's positive, you pick this solution, and if it's negative, you pick this solution. Okay? All right. So let's do this. So if EX net is given, then I know that EX net is the magnitude of E net times cosine of theta net, which means that cosine of theta net must be equal to the x component divided by the magnitude. Now let's calculate this ratio. So we found the x component to be minus 3.73 times 10 to 6. The magnitude is 2.38 times 10 to 7. The ratio is minus 0.1567. Okay, so then you go to your calculator and you find what is the arc cosine of this value. Sometimes this is shown as cosine minus 1. Okay, what is it? Okay, so if you do that, and then you have to be careful with the unit on your calculator. If you do this in radian, then your calculator should give you something like 1.728. And when you convert it to a degree, a unit, you will see that the answer is, so this is in radian. Okay, I'm gonna move these to this side. Now, when you convert this to degrees, which is basically either use your calculator or you remember that pi radian is half a circle, 2 pi radian is a full circle. So pi radian is 180 degrees. So you can calculate it like this if you want. You should end up with 99 degrees. Okay. It's really 99.02 degrees. Okay. Now, what you need to be careful here is that is that really the only answer? Because let's draw it. So far, this answer is telling me that if this is the x-axis, that's the y-axis. And I draw my vector, I'm going to use red. At 99 degrees, it would look something like that. So that would be my E net. This is 99 degrees. Okay, so it looks fine, except you have to still check if this is the only answer, or it's possible, like I showed you before, that maybe this is the answer, where this makes 99 degrees. Because your calculator is not going to know the difference between these two. So which one is the answer? So you're not really done until you figure this out. Remember the criterion here. The difference between these two answers is their y component. So I'm going to check, is the y component of E net positive or negative? I see here it's a positive number, right? So I don't need to do any more calculations. I already know that the only correct answer is this one. Okay, so then you're done, and you say that your vector is making 99 degrees with the positive x-axis. Now, one side thing. Let's say this was the solution. So hypothetically, let's say this was actually the solution. then what angle does this make with the positive x-axis? Well, it's actually, remember, you always open the angle in this convention from the positive x-axis. So you have to start your angle from this side, like that, which means that that angle in this hypothetical situation is actually 360 minus 99 degrees. So your angle with the positive x-axis is actually 261 degrees, not 99. So that's the difference, okay? But your calculator typically will give you numbers that are between 0 to 180 degrees, or maybe minus 90 degrees to 90 degrees, depending on the function that you input. So this is something that you have to take care of yourself by just thinking about the problem and looking at it and see if it makes sense. So again, I repeat, because the y component was positive, once we got 99 degree, we were satisfied with the solution. We picked the top one. But I could have done everything the same, and if the y component was negative here, I would get 99 again out of my calculator, but I would actually pick the lower solution. And if the problem asks you what is the angle it makes with the positive side of the x-axis, I would have to say it's 261, not 99. Okay? All right, I hope this was clarifying to a certain level. I think I covered almost every little aspect of solving this type of problem. That's why this took almost an hour. Obviously, it's not supposed to take you an hour to solve this problem. It's just that I was explaining, and it's slower to write it like this. You should really try to write as much as the stuff that I wrote down when you solve these problems until you are so confident that you don't make any more mistakes.